So y2 minus y1 over x2 minus x1, so 5 minus 3. At this point, we can use an equal sign because this fraction is truly equal to negative 6 over 2, which is negative 3. There are no units, so I'm just going to state my final answer is f prime at 4 is approximately equal to negative 3. That's it. Pretty straightforward. Ask questions if you got them. Give me a green check if you're good. And that makes sense. So here we're given a graph and a data set and also a context. The rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. The graph of r and a table of selected values of r of t for the time interval 0 to 90 are shown above. Use the data table to approximate r prime at 45 and show the computations that led to your answer. Indicate units of measure. Great. So r prime at 45, again, 45 is not in our data table. So we're just going to use the two closest points to it, which would be 40 and 50. And what we'll do is just find the slope between those two. So really what we're looking for, 45 would be about here, right? And what we truly want is the tangent at that point. But since we don't know that function, we can't do this analytically. So we're going to just make an estimate by finding the slope between the two closest points here and using that as the approximation of the slope of the tangent line, right? And again, we'll just use really careful notation. I'm going to say r prime at 45 is approximately equal to, and we'll just do the y values, so 55 minus 40 over 50 minus 40, which is 15 over 10, which is 3 over 2, or 1.5, right? And to get units, remember it's units of the y-axis over units of the x-axis. So the rate of fuel consumption has units of gallons per minute, and time is in minutes. So this is gallons per minute, or more simply, r prime at 45 is approximately equal to 1.5 gallons per minute squared. So it's almost like what we're finding is basically the acceleration of the fuel consumption over time, right? All right, Karen rides her bicycle along a straight road from home to school, starting at home at time 0 and arriving at school at time 12. During the time interval 0 to 12, her velocity is modeled by this piecewise linear function whose graph is shown above. Find the acceleration of Karen's bicycle at time 7.5 minutes and indicate units of measure. I think this is the first acceleration one we've done. So her velocity is measured in miles per minute, and time is measured in minutes. If we found a slope on a piece of this graph, what units would the slope have? You can go ahead and put it in the chat. What units would the slope have? So just think of a slope at some portion of this graph. Remember that slope is rise over run. And I agree with Olivia. The slope would have units of miles per minute squared, which miles per minute squared is what sort of a measure? What sort of a measure is miles per minute squared? Yeah, it's an acceleration. So basically, what we know is that the slope of a position versus time function gives us some sort of a velocity, either an average velocity if you find it between 2 points, or an instantaneous velocity if you find it at a single point. And now we know that the slope of a velocity versus time graph will give us an acceleration. And those rules will be the same. If you find the slope between 2 points, that'll give you an average acceleration over those 2 times. If you find it at a single point, that'll be the instantaneous acceleration. Another way to say that is that the derivative of position is velocity, and the derivative of velocity is acceleration. And we'll hit that more, but I just wanted to get that to you real quick right now. A third way to say that is that the second derivative of position is acceleration. So I can write that out. Usually we use s to represent position. So if s of t is position versus time, then s prime of t, that gives me velocity. S double prime of t, which is v prime of t, the first derivative of velocity, that gives me acceleration. All right. So now let's get to this actual question. They're asking for the acceleration at time 7.5. That is here. Well, sorry, Moline just G-chatted me in the middle of a class. So unprofessional, and it distracted me. If we have a linear function, then the instantaneous acceleration is the exact same as the average acceleration. And what I'm saying by that is that, right, the slope at this single point is going to be the same as the slope along the entire line. So what I can do to find that instantaneous slope is just choose 2 other points that I know their coordinates on that line and just find the slope between those. That'll be the same as the slope in the middle, right? So I know that that point is 8.2. I know that this point is 7.3. And so in this case, I'm just going to say that her acceleration at time 7.5 is equal to, and it's okay to use the straight up equal sign in this case because it's linear. So we're going to know exactly what the acceleration is. It's not an approximation. So is equal to, we'll just do 0.3 minus 0.2 over 7 minus 8, which is 0.1 over negative 1, which is negative 0.1, and this would be, as we said in the chat, units of miles per minute squared. We know our function is differentiable and has values shown in the table. We know that f and f prime are strictly increasing on the interval 0 to 5. So that means at no point will it dip at all. So it can kind of stabilize or flatten out, but it can't dip down, right? So that's going to tell us that we're going to have a positive slope of some kind. Which of the following could be a value of f prime at 3? So this is a good example to show how we should estimate a slope when we're given a table of values and the x value that they're asking for the slope at is included in our table of values, right? So, for example, we know what's going on at 2.8. We know what's going on at 3. And we know what's going on at 3.1. So normally when we were trying to estimate a slope at a specific point, we weren't given the actual point that we were trying to estimate. And so what we did was just find the slope between the 2 closest points, right? But in this case, we are given the point at which we're trying to estimate the slope. So then there may be two options. We could find the slope between 2.8 and 3, so that one, or we could find the slope between 3 and 3.1, which is that one, right? So which one do we want to do? The best thing to do is actually use both pieces of information. So find both those slopes, and then we'll take the average of those two slopes as our estimate. Does that make sense? So first, let's find the one I put in purple, which was the slope between 2.8 and 3. All right, so I'm going to do 39.20 minus 45 over 2.8 minus 3. I'm just going to pop that in my calculator. All right, I get 29. All right, then I'll find the slope between 3 and 3.1 in orange there. So that would be 48.05 minus 45 over 3.1 minus 3. And I get 30.5. And so again, the best thing to do is include both pieces of information. And so I'm just going to average those two values. So I'm just going to do 29 plus 30.5 divided by 2. And I get about 29.75. And so I would probably go with the closest value, which is D. Now this is kind of a poorly worded question because all of these are positive. So they all potentially could be the value of f prime at 3. It should probably say which is the best estimate of f prime at 3. All right. And we already talked about this in the warm-up, but let's practice it. I'm going to give you a second in your calculator. Find me the slope of the graph e to the tangent x minus 2 where it crosses the x-axis. So first thing we want to do is share my calculator. And then the second thing is plug our function into y1. So I'm going to do e to the power of tangent x and then minus 2, right? I believe it was minus 2. Let me double check. Yes. All right, I always like to just do a zoom 6, which is your standard window. Okay, so this is a periodic function. Now they say it crosses between 0 and 1. So they're talking about specifically this point here. So I don't need to see all that other nonsense. I'm just going to change my x window to just be between 0 and 1. Okay, that's the point I'm looking for, where it crosses the x-axis. The first thing I have to do is find that point. So we can do that in the calc menu. We'll just do second calc, and that's called a 0, where it crosses the x-axis. So I'm going to choose that option. It's going to ask me for a left bound. I just want to go to the left of where it crosses, hit enter. A right bound, I want to go to the right of where it crosses, hit enter. And as long as the 0 is in between those two arrows, it'll be able to find it. So I'll just hit enter. Boom. Now it gives you this long decimal that you think you have to write down. You actually don't have to write that down. One nice thing about your calculator is that when you use this menu and you calculate a 0, it's now automatically stored this whole number as X. So if I went out to the main window and just clicked X, enter, there you go. It's where that x-intercept was. It's the 0.606111937, right? So you can just use X in your calculation. So if I want to find the derivative, I would do, I'm just going to go back to my graph. I'll do calculate. I want the derivative, so the sixth option. I want it at X, which I know stored my 0.606119 blah, blah, blah. I'll hit enter. And my derivative, yep, is about 2.960. All right, any questions about that?
Sir Toller.
Go ahead.
Okay, I got all the way to that part.
Can happen. So where is the function absolute value of x differentiable? Well, there's really only one point that we need to worry about it not being differentiable, and that's going to be at the vertex. So an absolute value function like this is really just made up of two linear functions pieced together. So I can rewrite it as a piecewise function like this. The output of the absolute value function will be the opposite of the input when x is negative, right? So for example, if I plug in -3, my output is the opposite of -3 or +3, right? But it'll be the same as the input. It'll just be x when x is greater than or equal to 0. Now, both of those separately, you can take the derivative anywhere. What we need to worry about is what's going on at 0. If I try and look at what the derivative is at 0, I would need to use my limit definition as h approaches 0 of f of 0 plus h minus f of 0 over h. But we're dealing with a limit, so we actually need to look at this from both sides of 0. We need to look at it from the left and the right separately. So what I want to do, let's start out with looking at approaching 0 from the left-hand side. If I'm approaching 0 from the left, what piece of my function do I want to use? The top or the bottom? Yeah. If I'm approaching 0 from the left, I want to look at values less than 0. So I'm going to be using that top piece. So when I replace my functions here, I'm going to be using -x, right? So that's going to be the limit as h approaches 0 from the left of, I'm going to plug in 0 plus h to -x. So it's going to be -0 plus h minus, and then I'm going to plug in 0 to -x, which is still going to give me 0 over h. Simplifying this just gives me the limit as h approaches 0 from the left of -h over h, which is just -1. All right, so if I look at my derivative approaching 0 from the left-hand side, I get -1, right? Well, now let's look at it approaching 0 from the right-hand side. So if I go f prime of 0 from the right-hand side, Now what piece of my function do I want to be looking at? Top or bottom? Yes, Maisie, that's correct. You're spoiling it, but yes, it is going to end up being all real numbers but 0. So I'm just proving why it's not differentiable at 0. If we look at the limit as h approaches 0 from the right, we are going to use the bottom piece. So I'm going to be plugging in 0 plus h just to x, which will just give me 0 plus h minus 0 over h, which will give me the limit as h approaches 0 from the right of h over h, which is 1. So what you notice is that I get two different derivatives approaching 0 from the left and the right. And what we know is that if the limit from the left and the right don't approach the same thing, then the overall limit does not exist. So the overall derivative does not exist at 0. And if you look at the graph of the derivative, you get this second graph over here. And you can clearly see that at 0, the graph is undefined, right? Everywhere else, the derivative is defined. So this fails to be differentiable at 0. And what you can think of it is just like as slopes, right? I always said like the easiest way to think of a derivative is like picture a car driving along the curve and its headlights are on. Well, the direction of its headlights would then be the direction of the tangent at that point, right? Well, if we do that on the absolute value function, the tangent just goes, it's 1 on this side, it's negative 1 on this side, and they don't approach the same thing from the left and the right. Versus like on a smooth curve, your tangents are going to approach the same value whether you come from the left side or the right side. Does that make sense? All right. We're going to move forward. Last theorem. If f is differential, oh God. If f is differentiable at a point, then it must be continuous at that point. Extremely important. So anytime in the directions they tell you that a function is differentiable everywhere, that means it's also continuous everywhere. The converse of that statement is not necessarily true, as we saw in the last example. An absolute value function is continuous everywhere, but it's not differentiable at its vertex. So what I'm saying is just because a function is continuous does not necessarily make it differentiable. But if it's differentiable, it is continuous. It's like the statement, if I live in Phoenix, then I live in Arizona. That's true. But the converse of that is not necessarily true, right? If I live in Arizona, then I live in Phoenix, not necessarily. You could live in beautiful Yuma, Arizona, and go to the Yuma High School whose mascot is the criminal, the Yuma Criminals. That's a real thing. All right, any questions? Got a couple more just quick examples. These are just like visual examples. Okay, so how can a function fail to be differentiable? We saw that an example was the absolute value function. And we talked about this before. That's the property of local linearity. If the function has local linearity at the given point, it will be differentiable there. If it fails to have local linearity, it will not be differentiable. So how can it fail to be differentiable? You could have a cusp. That's a cusp. Or a sharp corner, like the absolute value function. You could have a discontinuity. So jump discontinuity. And the last thing, you could have a vertical tangent at a point and it would fail to be differentiable. Because remember what a derivative is, it's a slope. So if the slope is vertical, what's the value of a vertical line? It doesn't exist. It's infinite, right? This is an example of a function that is continuous, but not differentiable at the corner. That function would be differentiable everywhere else, but at that cusp, it would fail to be differentiable. So this just points out, right, if a function has local linearity, if we zoom in on this point, we can zoom in enough to make it look linear, it will be differentiable. If it fails to have local linearity, which is what corners and cusps do, no matter how much you zoom in on them, they still look like a sharp corner, it will fail to be differentiable at that point, okay? All right, a graph of the function is shown above. At which value of x is the function continuous but not differentiable? Go ahead and put it in the chat. What do you think? A, B, C, D, or E? I want it to be continuous but not differentiable. I agree. A, point A. So A is a sharp corner. So it's going to fail to have local linearity there. So it won't be differentiable. It is, however, continuous, right? Meaning as we approach A from the left and the right, the y values approach whatever this is, whatever y value that is. So it is continuous. It's just not going to be differentiable. At B, it's neither continuous nor differentiable because there's a discontinuity there. C is going to be both continuous and differentiable. There's definitely a slope right there. D is neither continuous nor differentiable because it's a jump discontinuity. And E is both continuous and differentiable. So your answer is A. All right. So it says this graph has a vertical tangent at the point 2, 0. So here. And horizontal tangents at the points 1, -1, and 3, 1. For what values on the interval -2 to 4 is f not differentiable? So what x values is this function not differentiable? Last thing. Are there any? Maisie says 2 and 0. Maisie, I agree with you. 2 and 0. 2 because it's a vertical tangent and they state that, so the derivative would not exist there because a vertical slope doesn't have a value. And then at 0 because there's this jump discontinuity. Everywhere else the derivative exists. They try to kind of throw you off by telling you that there are horizontal slopes here. Horizontal slopes do have a value. It's a value of 0, right? So the derivative does exist there.